Tse-Ming here with us today. Okay. Tse-Ming is an alumnus of our department. Okay, he got his Bachelor of Science degree in 1999 and Master of Science degree in 2004 here. Okay, then he went to Cambridge and got his PhD from Cambridge in 2009. Okay. In 2010, he went back to Cheng University, and he is now an associate professor in the Department of Physics in National Cheng University. His work is in this spintronic system. Okay, and recently he has a very exciting result. Okay, that he is going to tell us about. Okay, so the title of his talk will be all-electric spin transistor. Okay, let's welcome our speaker.
Thank you very much for the great introduction by Professor Zhou. And it's quite a great honor to come back to NTU. I always feel like this is a home. So, quite happy. I can see all the old friends and many teachers who used to told me lots of interesting beauty of the physics when I was doing my undergraduate master here. So today is my time to come back and share some of my work with you. So today I'll talk about the spin transistor and its all-electric one. So I'll begin my talk about talking what is the transistor. Because when I give a talk, sometimes I find some physicists don't really understand the transistor, although there are not many physicists don't understand, but some people are very focused on particle physics and some other stuff, may not aware of this. And I was told this is Colloquia. So I will try to talk all the basic concepts and not going into the detail. So if you have any question, just raise your hand any time to stop to interrupt my talk, that's fine. So what is a transistor? So we all know if we want to have the digital, so something digital, for instance, we take the mobile. Even you can have the computer, you have the digital camera, you have the listen to your music using like MP3. You always need a kind of like a chip. And if you use the iPhone 6, which I actually only also have this one, so you can find there's a very small chip, which is called the Apple's A chip. It's about this size in your iPhone 6. And you probably know this chip is fabricated by TSMC, which is a Taijidian in Taiwan, which achieved the 20 nanometer fabrication. And I think, is there anyone know how many transistors in this kind of chip? There's about 2 billion of transistors in this chip. And for each one, there's 20 nanometer, which means the gate, the length of the channel, which means from left-hand side to right-hand side is about 20 nanometer. And we know you can turn on or off this kind of switch to create the digital, and also if you have ever started microelectronics, you know you create all the amplifier and some differential amplifier and lots of this kind of stuff using this. So you can always say the transistor is the building block of the whole digital era. Okay. So let's look back. So what is the development of this kind of transistor, and also you can say the development of the whole semiconductor industry. So in about 1960, you can see for each transistor, the length is about 10 micrometer. And then for every 2 years, that is the Moore's law. I think most people have ever heard that. As Moore's law, they tell you every 2 years, the transistor size will halve, right? So you can see, so the people just predict this kind of trend. So you can see from like early 1960, and then for the number of atoms per bit per transistor, that's quite large. And as you continuously reduce the size of the transistor, you will expect in about 2017, for each atom, you have one transistor. And you know that's certainly impossible. And right now it's 2015. We are far from this because it's 22 nanometer, which means we're about like 200 times larger than a single atom. You can probably see the 22 nanometer transistor, which was released in the past 2 or 3 years ago. You can say this has some deviation from this kind of trend. And also, if you look at the whole semiconductor scattering process, You know about like 22 nanometer, which was expected in 2011 here, but it's actually realized in about 2013. And right now, TSMC and Samsung is trying very hard to fabricate the 16 nanometer or 14 nanometer, but the yield is still quite low. But so what is the end of this transistor? Most theorists will predict that the end of the transistor is probably the 5 nanometer, which means if you have the gate smaller than 5 nanometer, there is no way you can turn off the transistor, and you cannot control the 0 and 1 digital on and off this kind of thing. So I always say, when I'm giving a talk in IAMS, I use this. I say this is probably the theme of Moore's law, and possibly the semiconductor industry. And they told me this is certainly the end of Moore's law, but they deny this is the end of semiconductor industry. But I will say, yeah, you can still have the semiconductor industry, but it's not high tech anymore, right? So I'm in the physics, I was always making a joke to my students. So if you are still choosing electrical engineering, right, you're probably trying very hard to get the better transistor, whole electronic device, but you are doing physics. You try to find something to put everything very different and invent something more exciting. And this is the key of my talk. So I asked myself the question, because I'm not doing electrical engineering, so I'm not trying very hard to push into the 5 nanometer. I'm trying to find the other solution, okay, to resolve the whole problem. So I asked myself the question, what is the next generation of the device after the MOSFET? So the most interesting one is probably quantum computing, right? So there's a lot of people, some people are doing quantum information processing. So you know you use the superposition, you use the entanglement. But if you want to have the very long, like a coherence time and something like this, you probably need a very low temperature. Okay. And also, even though the computing power is very powerful, it's almost impossible to have the consumer product like your laptop in the like a 10 millikelvin, or not 10 millikelvin, 10 Kelvin, something like that. So it's almost impossible. So is there any other one? So the other computing functionality, or I would say the other method is probably called spintronic computing. So they use the spin, which is also a quantum number, but we do not use the superposition entanglement of this kind of wave function. So we only use the spin. And that has some advantage, like the spin switch time is faster than terahertz. So we know right now the transistor, if you look at your mobile phone, you probably know the functionality of the computing power. The frequency is about gigahertz, okay, right? 1 or 2 gigahertz. So the switching time, if that is terahertz, it could be thousands times faster, okay, than the traditional MOSFET that we are using right now. And also they could probably have the new functionality and also use less energy consumption. And some example is put in here. So you probably heard about the dry magnetic resistance, which won the Nobel Prize in 2007. And also you probably heard right now, I think it's probably early this year, they have some commercial product which is called STT-RAM, okay, which use the spin to store some kind of information. But if you look at all these products, you'll probably find most of the spintronic computing is relied on the memory, which is the storage. And if you want to have the whole computer, you need like information processing, which is the logic gate, right? And also you need the storage, which is the memory, hard disk, this kind of thing. Also you need the communication, so that's another story. So what is the logic gate for the spintronic computing? So the whole proposal is probably start from the dot-dot-dot spin FET. So later I will talk about the spin FET. But before going into the detail, I will need to show you this slide. So this is Nature magazine. I think they published in 2008. They choose about 23 milestones in the past 100 years. So you can see something quite familiar for even undergraduate students. You can see Tse-Ming effects thank a lot, like a spinning electron Dirac equation, this kind of thing. And you can also see like the most recent one, like NR, or like a dry magnetic resistance, this kind of stuff. And you can see there's proposal of this kind of spin field effect transistor, which was selected as one of the milestones, which is related spin. And you can notice this word is proposal, which means it has not been realized yet. Okay, so later, this is actually the outline of my talk. So I will mention what is actually the spin transistor and why the realization of it seems to be impossible. Because, you know, it was proposed in 1990s, and after 25 years, I'm standing here talking about spin transistor, which implies it has not been well realized, right? So I'll talk about what is the problem of that. And also I will mention what is the contribution, our contribution to the spin transistor, which will improve the functionality quite a lot. Okay, so any problem? Sorry, Okay, so again, any question, just stop me anytime. So what is a spin FET? So before going to a spin FET, we look at what is MOSFET. So the MOSFET, as I mentioned, if you ever studied microelectronics, that's quite easy. If you haven't, that's okay. Because, which means that you have the electron current, okay, flowing here, like a yellow spot. And you have the gate on top of this kind of channel, and of course you have the insulating, the dielectric layer in between the gate and this kind of semiconductor. So you can imagine if you have the current flowing from the left to right, and if you use the gate to create a barrier, so like the figure here, if you create a barrier and the electron energy is lower than the height of the barrier, the electron cannot go through the barrier, right? So this is like off state, which means there is no current can flow in from the left to the right. If you don't apply any voltage, for instance, if you leave the channel open, so you have the current going from the left to the right hand side, which will give you the on state. And for the digital, if you want to operate very fast, very quickly, you want to have the barrier and turn off the barrier, turn on the barrier very quickly. And right now, if you don't want the current to go through and very fast, the operation frequency is about gigahertz. Another problem is, we know we try to reduce the length of this, which means if the barrier become right now is 20 nanometer and become like a 5 nanometer, from the quantum physics, you know there's always tunneling current, right? So if you have the tunneling current, even though you have the barrier, the current can still go in from the left to the right, and which will give you the on state. So this is the reason why I mentioned there's no off state when you have the very thin barrier, the very thin gate. So different from the traditional MOSFET, the spin FET doesn't turn this kind of a barrier very quickly. So you can have the barrier for different spin, different barrier for different spin. So you can call it like a spin selective barrier. So in this cartoon, you can see if you have for spin up electron, you have very high barrier. So the spin up was blocked by the barrier. For spin down, there is no barrier. Okay, so the spin down can easily go into this kind of channel. Okay, so you have the on state for spin down electron and off state for spin up electron. And if you have the spin degenerate current, some of the spin up was blocked and some of the spin down was going through. So which is also the off state. It's on state. So how can we do that? So to create the spin selective barrier, your instinct would probably tell you use the ferromagnet, right? If you have ferromagnet for different spin, if you have the magnetization for different spin orientation, you have a different barrier. So this is the schematic diagram for the spin FET. So from this one, you have the dashed line is the barrier for the spin down electron. So the spin down electron can easily, there's no barrier for spin up electron. So the spin up electron can easily go into the channel. And all the spin down electron was blocked by this barrier, right? So if there is no spin free, all the spin remain as spin up. And for another barrier is in the anti-parallel position, align the injector barrier. So you will see all the spin down, so all the spin up was blocked by this barrier, and there is no current, which we call is off state. And if you can, for some electron, if we can quickly have a very short spin coherence time, which means the spin can be flipped in this kind of channel. And I just mentioned that the spin flip time could be like a femtosecond, something like that, it's terahertz. So if there's some spin was flipped to the other spin type, some spin can go in through the channel, through this barrier, so you have the on state. So you can use this to control the on and off very quickly without causing the problem, like you have the very short barrier and then some turning current can still go through. And here's a okay. So let's go to the cartoon on the top side. So this is the idea of the dot spin FET. We same as this one, we have the ferromagnet here and also have the ferromagnet here. So which means if this is spin down here, for spin out there is a very large barrier. So only spin down electron can go through this kind of contact. And the spin down electron can be rotated. So it's going, when it's moving along the channel, it's also due to the spin precession. So if it is precessed by like 2 pi or like 4 pi to be parallel to the magnetization of this ferromagnet, the current can go through this kind of ferromagnet contact. And if the spin has been rotated to anti-parallel to the magnetization of this ferromagnet, all the electrons will be blocked, right? So it will give you the no current alone, so which is the off state. So you can quickly switch the gate voltage. If you have the gate voltage, you can control the location angle. You can quickly change the on and off, and the rate could be as high as the terahertz. So yeah.
How do you detect the speed?
How do you detect the speed? If you put the current here, you put the current here. So if there is no current, if most of the current has been blocked, the current will be very small, which means the resistance is very large.
So current, you mean it detect charge.
It detect charge, yeah.
So it's not pure speed.
It's not pure speed, yeah. So you can also say spin polarized FET is not like a normal spin current. Yeah. Any other questions? Okay, so the next slide just tell you the evidence. But some people do the calculation. You can see the traditional like a FinFET is about like a gigahertz scale. Operating delay is like a 10 to minus 9. And you have the spin FET go to 10 to minus 12, which is the very high, like a terahertz scale. And also there is the energy it consumes, and it's also very low. And you can probably notice the graphene logic is also can operate very fast. But the problem of graphene logic is that there is no band gap. Okay, so the on-off ratio is actually quite low. So, but this can also be used for memory, but certainly not for large gap. So this is another cartoon. So let's summarize the basic idea of the spin FET because we will. Okay, forget about this. I don't know what happened. So if you have the ferromagnet, we inject the spin, and if you have the like a magnetic field, we know if you have the spin and if the spin is not keen or if not aligned to the magnetic field, you will start to do the spin precession, right? So if you do a spin precession, it rotate to like anti-parallel, it has been blocked. If you become parallel again, you can have the current. So to summarize the key of the spin FET, first you need a ferromagnet, and also you need a gate electric to control the spin rotation, which seems to be not that clear at the moment because we know only the magnetic field can rotate the spin, not the electric field. Right. So what can we do? So here comes the spin orbital coupling. So I think when you are studying the quantum physics in your undergraduate student level, you probably heard about like if you have the electron is orbiting your nucleus, you have the spin orbital coupling, right? So similar story. So if you have the electron moving along the x-axis, and if you have the electric field along the z-axis, which is perpendicular to your momentum, in the electron frame you will feel effective magnetic field, which is given by the cross product of the momentum and the electric field. It's given by this term. So this is the electrodynamics. It's quite easy one. If you put this into a Hamiltonian, you get something similar to your Tse-Ming effect. The only difference is this kind of Tse-Ming effect depends on the wave vector, which is your momentum. So if you have a different momentum, you will have a different magnetic field, which will give you a different spin gap. Okay. So in atomic physics, this electric field is provided by the Coulomb interaction between the nuclear and the electron orbiting along with it, right? So for solid state, for the material science, how can you create this kind of electric field? And you also require it to perpendicular to your electron movement. So here's the story. So if you have like this kind of semiconductor, 3-5 semiconductor, you can create a quantum wave along this axis. So this is Z axis, and you have a quantum wave here. So this is the energy gap, in an energy diagram. So you can imagine this is the band structure. So along the Z axis, if you have the quantum wave which is asymmetric, okay, so it's not like a flat quantum wave. There's some gradient here. So you know the gradient of the potential will give you the electric field, right? So you will have the electric field which is along the Z axis. And we know for the quantum wave, all the electrons can go into the page or out the page, which is in this kind of the XY plane. And this is the 2D electron. So all the movement of the electron is perpendicular to the electric field, which will give you the this kind of Rorschach magnetic field or Rorschach spin-orbit coupling, and it will give you spin precession or like a spin-dependent phenomenon. And if you want to have the spin precession, so we know first, you don't want the spin to align to the magnetic field, right? So this magnetic field could be the external magnetic field, could be this kind of Rorschach effective magnetic field. So you need a spin which is not parallel to this kind of Rorschach magnetic field. And if it is not, you'll start to rotate. And the rotation will determine by the energy gap, and this is called the Raman frequency. So it's given, if you ever study the quantum mechanics, you know the frequency is given by this. So the idea is if you have a spin which is not parallel to the y-axis, so go back to this. So you have the electric field along the Z. You have electron moving from the left to right, which is along the X. So you will have the Rorschach magnetic field along the Y, right? So if the inject spin is not pinned along the Y-axis, which you can lie anywhere in the XZ plane, you will start to rotate along the Y-axis. And if the rotation is going to like 2 pi, you will give a current. If it has become anti-parallel to a ferromagnet, it will block again. So the idea is actually quite simple. So this kind of phase shift is given by this equation, and you can simplify this. So you could probably find, for the spin angle, that is irrelevant to the momentum, because the time will have the momentum 10, and the frequency also have the momentum 10, and two of them will cancel each other. Okay. And here's one key to realize this. You need a ballistic, right? Because if you have the electrons being scattered in the middle, but it's moving from the injector into the collector, you will go in somewhere else, and also the spin randomization or like this kind of spin coherence will happen. So if you have the scattering in the middle, this will not give you the very good on-off ratio. So after we know the basic concept of the spin FET, let's go back to the whole history, how the development of that. Because we know it has been 25 years and it has still not been realized. So we must know the reason before we know how we can improve that. So it was proposed in 1990. So after 7 years, we know the first thing we need to electric field, or we need the gate to control the Rorschach, right? So to control this kind of alpha term, the alpha is relevant to this kind of electric field. So if you change the electric field, you change the alpha. You change the alpha, you change the phase shift. So this is the experiment. This is the first demonstration of how you can use the electric field to change the alpha value. So you can see the alpha is changing from like 10 to minus 12 to like 6 or 7, 10 to minus 6, minus 12. And the energy gap is like 4 to like 5 MeV. So it's only a small spin gap, not very large, but still. So if you put this into your spin FET, because we know if you want to have the delta theta, you need at least like pi, right? You want to rotate from the parallel to anti-parallel. So if you want to locate like have the pi or 2 pi, if you put the change of the delta alpha here, so we assume the delta alpha is 3 times 10 to minus 12, you probably need the L at least 2 micrometer. Okay, so which means if you need to grow material which is very clean, which have the very high mobility, very less disorder to have the mean free path from to go over 2 micrometer, and which is quite difficult. So this is one of the major reasons why it has to last so long. So there's other experiment. We probably don't have enough time, but in 2002, this kind of spin precision, because in atomic physics is quite easy, you can realize that. But in material science, there is always some phonon, some scattering, which can randomize your spin. So if you want to realize the spin precision, that is not that easy. So the first realization of the spin notation is in metal, which is, of course, the longer mean free path, and also using the external magnetic field. So you can see this kind of like, if it becomes a parallel, you have very large signal. If you go to the anti-parallel, it becomes a very low signal. So you can see this kind of, by changing the magnetic field, you can see this kind of stuff. And people also, I will go back to this later. So people also realize if you want to have a very long spin coherence length, that's probably not realistic, right? If you want to do a room temperature device, that's almost impossible to have such a long mean free path. So people also propose other, like this one, non-ballistic spin FET. Okay, so this is a very important paper. So if you are interested, you can go into this one. So this is another project. I will go back to this later. So in semiconductor is what realized in 2007, similar story. So let's skip that one. So in 2009, about 5 years ago, this is quite important one. It's published in Science. So people use the gate, not magnetic field. You actually use the Rorschach, which means you use the electric field to control the spin rotation. So the similar device, you have the ferromagnet is here. You have another ferromagnet. You have a gate on top of that. So we know the electric field is along the Z, right? Because the asymmetric quantum wave. And if you have electron moving along the X, you know you have the magnetic field, the Rorschach magnetic field along the Y. So if you have the ferromagnet pin along the Y, the electron being injected from the ferromagnet is always pinned along this kind of Rorschach field, right? So of course you don't expect to see any spin precision. So if you look at the data, you will see there is no spin precision here. So if you do something interesting, if you apply external magnetic field to change the direction of the magnetization of this ferromagnet. So if you can change this to the X direction, so this is not parallel to the Y direction, and so the electron being injected is X and can start to rotate along the Y. Okay, so when you go to the anti-parallel, there's no current. When you go to the parallel again, you have the current. So by changing the gate voltage, you change the electric field. You also change the spin precision frequency, which means you will get this kind of test. You have the parallel, anti-parallel, parallel, anti-parallel, parallel, anti-parallel. Okay. So this will give you the arm of. Okay. So this seems to be quite successful, right? Because you have the first experimental demonstration of this kind of spin FET. It's very similar to the traditional dot-dot-dot spin FET, as we have realized. So what is the problem? If you look at their data, you will find the on-off ratio is actually quite small. So you'll see this is a delta V. This is not actually current. It's just the data just extract the variation, the small modulation along the current, on top of the current. So this kind of small modulation is only giving you like a 0.010 ohm, which is almost not useless, okay, when you are doing the electronic device. Because you need a very large on-off ratio to give you a larger gain. You want to turn the current off, it's strictly off. And if you want to have on, it's strictly on. So when people are doing this field, we start to wonder, so what is the problem then? Whether this is like an end of the dot-dot-dots. Because we have already, like what I mentioned here, they have already have a very long mean free path in the low temperature, which is about like 1.6 micrometer. and the distance is only like 1.2, 1.6.